Imagine teaching one giant AI one new job. With full fine-tuning, every part can change, so the new task gets another full model copy. In one example from the original GPT-3 study, that copy was about 350 gigabytes. LoRA stores the new task differently. In that same example, the large base model stayed shared, and one LoRA task update was about 35 megabytes. Compared with 350 gigabytes, that is about 10,000 times smaller. LoRA keeps using the giant model. The new lesson fits in the tiny orange piece beside it. How can a file this small change what the giant model does? We can find out by opening one part of the model and watching what changes. Open that blue piece, and inside is a giant table of numbers. This one has 4,096 rows and 4,096 columns, so it holds 16,777,216 numbers. A table like this is called a weight matrix, and full fine-tuning can change every number in it. LoRA freezes this giant table. Frozen means its 16,777,216 blue numbers stay fixed while the new task is learned. Beside it, LoRA builds a detour from two thin tables. The first squeezes 4,096 numbers down to 16. The second spreads those 16 numbers back to 4,096. That narrow middle is called rank 16. These two thin tables contain 131,072 trainable numbers altogether. The giant square table contains 16,777,216. So this rank 16 LoRA path trains 128 times fewer numbers for this weight matrix. The same input travels through both paths. The frozen blue table gives the original result, while the two orange tables make the learned change. Adding them gives the adapted result. LoRA is this small added change beside the frozen model. In one simple atom setup, training a model number needs more than the number itself. It also keeps a gradient which points toward a change and two memory values that help guide later changes. Together, these pieces are model state. Full fine-tuning keeps the full bundle for every model number, while LoRA keeps the training extras only for its orange path. Now use a model with 7 billion numbers. In this simplified atom accounting, full fine-tuning needs 112 gigabytes of model state. Keeping the base frozen in 16-bit and adding LoRA numbers equal to 1% of the base needs 15.12 gigabytes. Both totals leave out activations and temporary buffers. The smaller model state still includes the blue base. Every input travels forward through it, and a learning signal travels backward through it toward earlier layers. LoRA skips the calculation that changes the blue weights, while much of the blue path keeps working. Training also saves temporary results called activations. It needs them later to work out the backward learning signal. LoRA still carries many of these saved results, so total memory is larger than the 15.12 gigabytes model state bar. The orange task file and trainable state shrink sharply. Total memory still includes the blue base and activations, and training time still includes much of the blue calculation. Fewer trainable numbers bring real savings, but total memory and time do not fall by that same 128 times. The next limit is how much learning the orange path can hold. That rank 16 middle gives the orange path 16 independent lanes for change. A higher rank adds more lanes, so the patch can combine more kinds of change. The patch can act only where we attach it. An orange path on one layer can change that layer, while layers without one stay on the blue base alone. The chosen places are called target layers. In one Llama 27B code instruction test, rank 256 LoRA reached 49.8%, and full fine-tuning reached 49.7% at their best reported points. In this setup, the orange paths covered all the model's linear layers. On this score, the patch had enough room. The same 7B model also learned from 20 billion code tokens. At the end, rank 256 LoRA scored 22.4%, while full fine-tuning scored 26.3%. Even the widest LoRA tested finished behind on this task. A newer lab study on Llama 3 and Quen 3 found a similar boundary. On its tested post-training data, LoRa could track full fine-tuning when rank was high enough and orange paths covered important layers. Lower ranks fell behind once the dataset carried more information than the adapter could hold. In that opening example, the 350 gigabytes base still holds the original model and does most of the work. The 35 megabytes LoRa file stores only the targeted change for one task. The base result and the small change are added together, which is how a file 10,000 times smaller can change what the model does. LoRa is a good fit when one shared model needs several focused specializations. Each task can keep its own small orange patch, while every task reuses the same blue base. A broad rewrite can need more change than a small patch can hold. Full fine-tuning has room to change the whole model, so it is the better fit when the new lesson must reach widely across it. Learning without retraining everything means keeping the shared model frozen and training the small change beside it. The blue base remains the model, and the orange patch carries the task.